Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are going to present wave, wave equation and Fourier series. Two important materials tools are used in this assignment: Fourier series and the wave equation. What is Fourier series? A Fourier series is the way to write a complete function as sum of simple sine and cosine wave. This is very useful because some functions are hard to work with directly. But when we broke them into similar sine and cosine parts, the problem becomes much easier to solve. Why this is important? Both questions show how Fourier series help engineering solve real problems, whether it's heat distribution in materials or vibration in mechanical system. These methods are widely used in fields such structures, engineering, electronics, and manufacturing.
Assalamu alaikum warahmatullahi wabarakatuh. Today we'll solve question 1, part A, B, and C. For part A, the step 1, write the formula for cosine Fourier series. Tx is equals to an divided by 2, the integration from L to 0, tx cosine m by x dx. A naught is equals to 2 over L, the integration from L to 0, tx dx. An is equals to 2 over L, the integration from L to 0, tx dx. Bn is equals to 0. Step 2, we have to find A naught and An. We already know L is equals to 1, so we should find A naught. That's equal to 2 multiplied by the integration from 1 to 0, 3 exponential 2x dx. 6 multiplied by the integration from 1 to 0 exponential 2x dx. We already calculate exponential 2 that give us 7.389. So we multiply 6 by exponential 2 over 2 minus exponential 0 over 2. We got 6 multiplied by 3.69 minus 0.5. We got 19.14. For An, we use the formula 2 multiplied by the integration from L to 0, 3 multiplied by exponential 2x cosine m by x dx. And we already know A is equals to 2, B is equals to m by. So we got exponential 2x multiplied by cosine m by x plus m by multiplied by sine m by x over 4 plus m by squared from 1 to 0. So we already know cosine nt is equals to minus 1 to power of n, and cosine 0 is equals to 1. And we already know sine m by is equals to minus 1 to power of n. Oh, sorry. Sine m by equals to 0. Sine 0 equals to 0. So we got 6 multiplied by 2 exponential 2 multiplied by minus 1 to power of n divided by 4 plus n squared by square minus 2 over 4 plus n squared by square. 12 multiplied by exponential 2 times minus 1 to power of n minus 1 over 4 plus n squared by square. So we substitute the values into the formula. We got the final answer is 9.595 plus 12 multiplied by exponential 2 minus 1 over n minus 1 to power of n minus 1 over 4 plus n squared by square cosine m by x. So this is the answer for question 1 part A. For part B, we already get an is equals to 12 times exponential 2 minus 1 to power of n minus 1 over 4 plus n squared by square. So we need to calculate a1 and a2. For n equals to 1, minus 1 over 1 is equals to minus 1. Minus 1 to power of 1 is equals to minus 1. And exponential 2 is equals to 7.389 pi squared is equals to 9.8696. So we use the calculator to calculate a1 that give us minus 7.259. For n is equals to 2, minus 1 to power of 2 is equals to 1. Exponential 2 is equals to 7.389. Pi squared is equals to 9.8696. So we use the calculator to get A2. I got 1.7639. So we use the formula for the Fourier series. We got Tx is equals to 9.595 minus 7.2585 cosine by x, because n is equals to 1, plus 1.7639 cosine 2 pi x, because n here is equals to 2 and n here is equals to 1. So if x is equals to 1, t1 is equals to 18.61, because we use the calculator to get t1. But t1 is equals to 3 exponential 2, that's equals to 22.17. So if we add more values of n, we will get more appropriate values for the series. So this is the answer for question A, part B. For part C, when the boundaries are insulated, the derivative of t or dx dt over dx is equals to 0 when x is equal to 0 and x equals to L. By using cosine series, d cosine n by x over L dx is equals to minus n by over L sine n by x over L. So this is the differentiation for cosine n by x over L. So when x is equal to 0, minus m by over L times sine 0 is equal to 0, because sine 0 is equals to 0. You know it already. When x is equals to L, and we already got the value of L, that's L is equals to 1. So minus n by over L sine m by is equals to 0, because sine m by is equals to 0. So cosine series established the condition dt over dx is equals to 0. Thus, the cosine series is better for insulated boundaries. So this is the answer for question A, part C. So Muhammad Khalid will complete the next question.
So hello everybody. I will continue with you question 1 bar C. In this question, we have to determine the half range for a sine series, and in this case, the time domain equal to sigma from infinite to n equal 1 bn multiplied by sine m by x. And also in this case, we don't have to find the value for a0 and a1 because they are equal to 0. And bn equal to, so in the first step, we have to substitute the values of tx and l equal 1 to find bn. So bn equal 2 over l, the integration by above from L to 0, tx multiplied by sine m by x dx. So when we substitute the values, 2 over 1 equal 2, and we substitute the value of tx by 3e to the 2x sine m by x dx. The next step, we will take the 3 out and multiply it by 2 to get 6, and we will got this formula. Step 2, we have to use the ordinary integration by part because tabular method can't work in this case. So the ordinary integration formula is the integration for e to the exponent ax multiplied by sine bx dx equal e exponent ax multiplied by a sine bx minus b cosine bx over a square plus b square. And we have the value for a, which is 2, and also the value for b, which is 2 pi. Therefore, we will substitute these values in the formula, and we will get this answer. Step 3, we will have the integration by part. When x equal 1, sine m by will equal to 0, and cos m by will equal minus n to exponent n minus 1 exponent n. So after solving the integration, we will get this value. The second step is when x equals 0, sine 0 will equal 0, and cosine 0 will equal 1. So we're gonna So after solving it again, we will get this answer. After subtract the values we have got, we will get this solution, which is n by multiplied by 1 minus e exponent 2 multiplied by minus 1 exponent n over 4 plus n square by square. So bn in this case will equal 6. We have to multiply that 6 in the multiply by m by multiplied by 1 minus e square multiplied by minus 1 exponent n over 4 plus n square by square. Step 4, we have to substitute bn into the time domain formula. This is the time domain formula in the half range Fourier series. After substitute bn, we will got this answer: sigma infinite to n equal 1, sigma infinite to n equal 1 multiplied by 6my multiplied by 1 minus e2 multiplied by 1 minus 1 exponent n over 4 n square by square multiplied by sine m by x. And this is the answer for part D. Part E in question 1 asks us when the sine series is more appropriate. The sine series is the natural choice when the boundary condition is differential. The function value itself, not its derivative, is fixed, typically 0. At the ends, t0 equals 0 and tl also equal 0. In mechanical systems, this corresponds to situations such as a rod string whose inertia held fixed at a reference value, like a displacement equals 0 or a temperature clamped to fixed reservoir value, rather than insulated one. Since sine m by x over L equals 0 at x equals 0 and x equals 1 automatically, the sine series is the correct expansion whenever the physical boundary force forces the quantity itself to vanish at the ends.
Question 2, part A asks us to identify the boundary and the initial conditions. So in this case, the boundary condition is a string fixed values at both ends for all time. So u0 t equals 0 and u30 t equal to 0. The initial condition in this case is an initial displacement, like the plug shape. So ux0 equal 3 over 10 multiplied by x for 0 less than or equal x or less than or equal 10. Also for ux0 equal 3 multiplied by 30 minus x over 20 for 10 less or equal x less or equal 30.
For part B, I'm solving the wave equation utt equals 9uxx on an interval from 0 to 30. And using the separation of variables, the string is fixed at both ends and starts from rest plucked at x equals 10 and height of 3. So first, I assume the solution can be written as a product of u of x and t equals x of x times t of t. Substituting this into the wave equation and dividing both sides by 9xt, I can get two sides that each depend on one variable. Since they must be equal, both sides equal the same constant, which I call a negative lambda squared. So then we get this separation gives me two ordinary differential equations, one in x and one in t. So applying boundary conditions, the x has a general solution a cosine x plus b sine of x. Applying the boundary condition at x equals 0 forces a to be 0. At x equals 30, b sine 30 must equal 0 here. For a non-trivial solution, this means 30 equals n times pi, giving the eigenvalue n equals n times pi over 30. Step 3. Solving for tt. With lambda known, the t equation becomes t double prime plus n pi m pi over 10 squared t equals 0. The general solution is c and cosine of n pi t over 10 plus d and sine of the same. Since the initial value, since the initial velocity is 0, d must equal 0 for all of n. Then, by superposition, I sum all the mods. The general solution is a series of sine-cosine products with a coefficient of b of n. Find coefficient b of n.
Find coefficient b of n from f of x. The initial shape is a triangle, rising linearity from 0 to height 3 at x equals 10, then falling back to 0 and x equals 30. I use the Fourier series sine series formula, splitting the integral at x equals 10. After evaluating, I get the closed form coefficient, as you can see here. Next, putting it all together, the complete solution is this series. The coefficient 27 over n pi squared multiplied by sine n pi over 3 over n. Putting it all together, the complete solution is this series. 27 over n pi squared multiplied by sine of n pi over 3 multiplied by the sine cosine mod. Notice that sine of n pi over 3 equals 0 whenever n is multiplied of 3. So the third, sixth, ninth, here you can see. So the third, sixth, and ninth of harmonics all vanish. This is because the string was plucked exactly at 1/3 of its length, a well-known result in acoustics. As a quick check, we can here. As a quick check, at x equals 15 and t equals 5, every term in the series has a factor of sine, you can see here, as a factor of sine n pi over 2 times cosine n pi over 2, which equals to 1/2 sine n pi, which is 0 for all integer n. So the midpoint at the equilibrium at n. So the midpoint is at equilibrium at t equals 5 seconds.
So the midpoint is at equilibrium at t 5 seconds. This makes sense physically. T equals 5 is exactly 1/4 of the fundamental period of 20 seconds. Thank you, and this was the sine series.
Hello, my name is Abu Bakr Idris. I will conclude and I will continue. So, in conclusion, and after across both problems, the choice of Fourier series was dictated by physical boundary conditions, not convinced. In question 1, the insulated rod had zero flux boundaries, so the cosine series fit naturally, which is zero slope at the ends, forcing a sine series instead produced Gibbs phenomenon, overshot and ripples, because sine series impose zero value at the boundaries, which contradicts the insulate rod's actual physics. In question 2, separation of variables split the wave equation into two ODs, fixed and boundaries, plus the released from rest condition gave a cosine in time solution. The simulation confirmed the sine series like this correctly builds a triangular block shape, and the midpoint returns to zero displacement at t equal to 5s, a quarter period, and this exactly as predicted analytically. So overall, this assignment shows that boundary and initial conditions are not just technical details. They determine the mathematical from from of the solution. Sorry, and the Python simulations confirmed our analytical results, matched real heat and wave behavior.